Hello everyone, and welcome to a discussion of gravitational potential energy. Now we've already discussed gravitational potential energy, but when we did that, we were always looking near the surface of the Earth, where we could consider the gravitational field to be a constant. Right? And therefore we ended up with a gravitational potential energy equation of mgy, right, which we could use. But we now know that the force of gravity, and therefore the gravitational potential energy, is dependent on the inverse square of the separation distance when we get significantly far from the center of the Earth, right? Significant distance more than the radius of the Earth, right? So how then would the gravitational potential energy work in that case? Well, consider our apple, right? A distance r from the center of the Earth, which is significantly more than just the radius of the Earth. Let's start out by considering where would that gravitational potential energy be zero? Where would it no longer have the ability to produce any change, right, due to its location in a gravitational field? Now, when we were looking near the surface of the Earth, we always called the surface of the Earth zero. But does that make sense in this case? Well, consider the law of universal gravitation. Right? I hope it makes sense to you that the gravitational potential energy would be zero when the force of gravity is zero. Right? Because then it has no ability to produce change because there's no force acting on it. Right? So when would the force of gravity be zero? Well, big G is a constant, the gravitational constant. This is the mass of the Earth. This is the mass of the apple. Those are both constants. So the only thing that could change here would be the separation distance. Note that it's squared and it's on the bottom of the fraction. So what does the separation distance have to be to make the force of gravity zero? And if we think in a calculus-y way, the force of gravity, and therefore, three dots, right? Therefore, the gravitational potential energy approaches zero as r approaches infinity. Right? When the planet and the apple get infinitely far apart, you put infinity at the bottom of a fraction, it equals zero. The force of gravity shrinks to zero. And infinity is really the only place where the force of gravity would technically drop all the way to zero. Now, sure, if you're really, really, really far apart, it might be so small that you can't even notice it. But if you want to be technically mathematically accurate here, it's when r approaches infinity that the force of gravity, and therefore the gravitational field strength, would shrink to zero. Now, this has some weird consequences, because if we're going to define our zero as being at a position of infinitely far away from the Earth or whichever planet we're looking at, right, that means we are always under that. Right? It's kind of the opposite of when we use the surface of the Earth and we were always above that. Now we're always under. We're going to see that have a little effect on our final equation. So let's now do a little calculus and create an equation that would allow us to calculate the gravitational potential energy of this apple at a distance r from the center of the Earth. Okay, something smaller than infinity, right? R. So we have to remember here that, of course, the force of gravity is the only thing acting on the apple. We know from our study of potential energies that we can calculate a potential energy by taking the negative integral of the force with respect to position. It's the area, the negative of the area under the curve of the force position graph, right? So in this case, we have to do the integral. Well, the force in this case is the force of gravity. I'm going to change the x to a y because we're dealing with vertical, right? So just like the y that we used originally in the mgy, right? Same kind of y here. So it's the height, essentially, right? And then our limits of integration is we're gonna start at infinity and end at r. Start at infinity, so we're going to start the apple at infinity and drag it to r, and then say, okay, how much gravitational potential energy does it have? All right? So, it's the negative of that integral. Well, the force of gravity is a negative big G mm over y squared. We're using y instead of r here, right? It's negative because it's an attractive force, remember. Right? It's a negative force. It's attractive. So the negatives cancel. Big G, the mass of the Earth, and the mass of the apple are all constants, and they can be pulled outside of the integral. So we actually have a fairly simple integral to do. It's the integral of 1 over y squared with respect to y from infinity to r. 1 over y squared is, of course, y to the negative second. So to take the integral, we add 1 to the exponent, divide by the new exponent. Negative 2 plus 1 is negative 1. So we have to multiply by negative 1. We get a y to the negative 1, which is 1 over y. So the integral of 1 over y squared dy is negative 1 over y. Right? Nothing fancier than that. And we have to evaluate it from infinity to r. Well, to do that, we evaluate it at the upper limit, r, minus evaluating it at the lower limit, infinity. Well, what's 1 over infinity? 0. Right? That was the whole reason, right, that we said, hey, yes, infinity would be 0 f of g and therefore 0 eg. That leaves us with a gravitational potential energy at any distance r from the center of the Earth or the center of whatever planet we're talking about, or the sun or something like that, of negative big G, mass of the planet, mass of the object, over r. Notice this looks a lot like the force, but not quite, right? It's r, not r squared. This will give us units of Newton meters or joules of energy. Now you might be saying, wait a minute, why is it negative? Well, it's negative because of what we defined as 0. We defined infinity as being 0. And so we are always under infinity, right? And therefore negative. Now, we always used to define the ground or the lowest point as being 0, and therefore we lived above it. And so when we were doing MGY, constant gravitational field, near the surface of the Earth, right, we always had positive amounts of EG. So this is strange, but as we do these planets and things and orbits, we always talk about gravitational potential energy as being negative. We could have done that before. It would have been weird to do, but let's say when we were in our room, we called the ceiling 0 instead of the floor 0 EG. Well, if we called the ceiling 0 EG, we always would have been under the ceiling. And so we technically would have had a negative amount of EG. I mean, I don't know why we would want to do that, but we could, right? Here we're doing it because of how this actually works, and that it shrinks to 0 at infinity, and we live under infinity away from the planet, so we have to have a negative EG. And you got to be really careful here, because EG is a scalar. Energy is a scalar. This is not a vector. This is not a direction. Okay? This is scalar negative. So notice, as you get closer to the planet, right, r shrinks. R is the distance from the center of the Earth to the center of the apple. So as we get closer to the Earth, r gets smaller, which means the fraction gets bigger, but it's negative. And in scalar algebra, a bigger negative is actually smaller. How do you like that? Right? Which means that the same kind of pattern holds. The closer we get to the Earth or the planet, the less gravitational potential energy we have. It just becomes more negative. And again, scalar algebra, not vector algebra, because this is energy, and energy is an amount of ability to produce change. It doesn't have a direction associated with it. Right? Dot products as opposed to cross products, scalar products as opposed to vector products. All right? So you okay with that? So you got to be really careful. This does some weird things. We're gonna do a big old example problem in our next video where this is going to come into play. All right, and the scalar aspect of it's going to come into play. All right, so here is our new equation for gravitational potential energy at a significant distance from the center of the planet. Okay, negative big G, mass of the planet, mass of the object, all over the separation distance. It'll be in joules, but it's always negative because we live under infinity, which is what we defined as 0. And just because it's scalar, bigger negatives are smaller. Smaller negatives are bigger. Okay, so let's talk about one specific case where we can use this. All right, and like I said, we'll do a bigger example of orbiting and some things like that, some elliptical orbits and stuff tomorrow. And this is what's known as escape speed or escape velocity. Escape velocity or escape speed is the speed you need to escape the gravitational effect of a planet or the sun or a solar system or whatever you're looking at. Okay? So this is the initial speed a projectile of mass m would need to completely escape from the gravitational force of a planet or system of planets, or sun, or something like that. Okay? Notice we're calling this a projectile. So, in other words, it's got to have this speed, and because of gravity, it's going to slow down as it goes further away, right? But that's the speed it needs, so without being able to shoot rockets along the way or make anything more complex, all right? What does it have to be moving in order to escape the gravitational force? Now, let's talk about what that means, okay? If it's going to escape the gravitational force, right, where does it have to go? Well, it has to get to infinity, like we just talked about, right? Because at infinity, the force of gravity shrinks to 0. So if this is the slowest speed it could reach infinity, right, when it gets to infinity, it will stop at infinity. And I know this is weird, but it's calculus-y kind of thought process, right? So it's going to reach infinity and stop. Because if it's still moving at infinity, it could have been going slower initially. You with me? Right? So it's got to get to infinity and stop. This means that if we look at the total mechanical energy, which is the sum of the kinetic and the gravitational potential, right, at infinity, both EK and EG will be 0. Because it will stop and will be at infinity, where the force shrinks to 0. So at escape speed, when you get to infinity, both things will be 0. And that means the total mechanical energy will be 0. Right? So the final total mechanical energy will be 0. Or if you will, the final energy, right? So if we're going to do a little conservation of energy problem here, and our final is at infinity, both kinetic and gravitational will be 0. So if we're going to put the projectile of mass m and the planet it's trying to escape from inside of the system, then the system is isolated and therefore the total amount of energy doesn't change. We would have changes as it gets further away. We would have changes in EK and changes in EG. Every change in is a final minus initial. And as we just discussed, if we're talking escape speed, this is the slowest speed it could have and still escape from the gravitational field, which means at infinity, right, EKF and EGF will be 0. And that means, in this case, your EKI has to be equal to the negative of your EGI. Well, we know math models for each of those now. Your EKI would be 1/2 m times what I'm going to call the escape speed or the escape velocity squared. So that E here doesn't stand for Earth, it stands for escape. Okay? Over here, as we just derived, our gravitational potential energy will be negative big G, mass of the planet, mass of the object, over their separation, R. Note, the negatives change, which is good because kinetic energy can never be negative, so it can't be equal to a negative, right? And remember, your EG is negative because we've set our 0 at infinity, and we live below infinity. Note the mass of the object cancels. So theoretically, it doesn't matter whether you are shooting off a small satellite, right, or a space station. If you want it to escape from Earth's gravity, they have to get to the same speed. But you might be saying, well, wait. The mass has got to count for something, and it does. It would be much harder to get a space station to that escape speed, right? Because F equals ma, right? To get the acceleration you would need to get to the escape velocity, you would need a much bigger force because there would be more mass, right? But what this is saying is you need the same speed at the end to get it to escape, okay? More mass means you have more kinetic energy at that speed, but more mass also means you have more gravitational potential energy, so they cancel out. So we solve, and we get an equation for the escape velocity. Square root of 2 big G mass of the planet over r. Don't confuse that. That's not the mass of the object. This is much like our orbit equation that we derived the other day. It's the mass of the planet, not the object, right, over r. Of course, again, you might see this a lot in proportional thinking kind of ways. What if I double this or double that? What's going to happen to the escape velocity you would need? Okay, but you can also plug and chug numbers through that. And by the way, the AP expects you to be able to do this proof using our new gravitational potential energy equation, right? And explaining why the final of both is 0, because at infinity, right, the force shrinks to 0, therefore the gravitational potential energy shrinks to 0, and it would stop at the escape speed. Right? Anything faster than the escape speed, you would still have kinetic energy left. So you ought to be able to do this proof, and if you can do it quick, right, you can get to this equation even if you don't have it memorized, because I do not believe it is on your equation sheet. And again, capital M is the mass of the planet or system you are escaping. So the more mass of the planet, yeah, you got to go faster. So what's the escape speed from the surface of the Earth? We are going to neglect air resistance here, because that would make things way harder. So we're going to escape from the surface of the Earth, not worrying about air resistance. Right? Then our equation becomes mass of the Earth and radius of the Earth, because we're right at the surface. Plug in the numbers we've used in other problems, or derived. Don't forget the big G here, 6.67 times 10 to the negative 11th. Note the units. Right? Let's see here. We get a... Well, it all cancels out, and we should end up with meters per second. We do, I guess, in here. Right? We get this meter squared cancels that meter. This kilogram cancels that kilogram. So we're left with a meter over a kilogram, but a Newton is a kilogram, meter per second squared. Right? So it all works out. So plug everything in. You get about 11,200 meters per second, which is about 11.2 kilometers per second. If you were to look this up somewhere, they'd probably write it this way. Or, in English units, it's about 25,000 miles an hour. You got to get something going pretty fast to be able to escape the Earth's gravity. Mind you, this neglects all the other planets and especially the sun, right? So this is if the Earth was just by itself, right? No air resistance, all of that. So this is a really fast speed, right, to get to. So then how, could you help things? Well, you can't really change the mass of the Earth, but you could change where you launched from. So maybe if you were launching from an orbiting space station, you might, A, get rid of air resistance if you're outside of the Earth's atmosphere, really get rid of air resistance. And secondly, your R would grow bigger, which would make the fraction smaller, right? So you wouldn't need as much speed. And then, of course, there's can you pick up any speed along the way, right? How did Voyager, one of the satellites, get away from the solar system? Well, they did things like dip it past a planet, right? Whip it around a planet to pick up speed and those kinds of things because it didn't have boosters, right? Or you could fire your rockets if you still had that. But then you got to bring the fuel, and that means more mass, and that makes it harder to get up to this speed because F equals ma, and you see the problems, right? So this is a little thing called escape speed, sometimes known as escape velocity for short. And you could see it, of course, on an AP test. If you know the equation, you can use it. If they ask you to derive it, well, then you got to derive it. Right? It's based on the mass of the thing you're escaping from, the mass of the planet or system, and the separation distance to start out with.